So in this lecture, we're going to talk a little bit about the notion of a finite state machines. The whole idea is that the modern computers can be thought of as a machine with a finite number of states. Usually you call them S0, S1, S2, and so on, with some transition based on the alphabet it reads. If the input reads B, for example, if you're in state S0, and it will stay in S0, and so on. So we'll talk more about these things in the upcoming slides. So I'm going to skip through this one and get into some of the notation, finite state machines, finite state automata, and deterministic finite automata, and so on. So a vending machine is a good idea to simulate using a finite state machine. So let's see what we can do there. So suppose you have a vending machine that accepts only the inputs of 25 cents. So the input alphabet, or what we usually call like alphabet, would be just the 25 cents coins. So let's assume that this vending machine gives a drink if you give 50 cents. And so we're going to design a machine like this. This machine will have three states, S0, S1, and S2. And we call this state the accept state. And we call S0 the start state. And because we only have one symbol that allows you to go forward, for example, if I put a 25 cents, I'll be able to go to state 1. If I put another 25 cents, I'll be able to go to state 2. So by putting 25 to 25 cents, I've gone to a state where a drink can be dispensed. So I can get a drink here. So once the drink is dispensed, I can go back to S0 and wait for that. So you can see how simple this machine is and the way we designed that. Now obviously I could expand the alphabet to include more coins, for example 5, 10, and 25. Now if I do that, then I'll have to increase the number of states in order to accommodate all the possible combinations of these coins before we get to the 50 cents. So another way to think about these states is to think that if you're in state 0, that means you haven't put any money into it, or the vending machine has no money. If you're in state 1, the vending machine has 25 cents. If you're in state 2, the vending machine has 50 cents. So formally, we can define a finite state machine as a machine with a number of states. So let's say the set of states, usually denoted by S0 through, let's say, Sn, and of input alphabet. So alphabet can be the binary alphabet. Let's say it's 0 and 1. And a transition function that might say if you're in S0, if you get a 0, you go to S1. If you are in S0, you get a 1, you stay in S0, and so on. So you can define these transitions for each of the tables. And an output function G that assigns each state input pair and output an initial state 0. So for example here, we could say if you're in state 0 and you get a 0, you go to state 1, but output the number 1, something like that. Same thing here. If you're in state S0, you get a 1, you go to you stay in S0 and output is 0. So we could design machines using this kind of rules that will allow the machine to function. So let's take a look at a simple example of a machine. Let's suppose that S0 is the initial state and either S1 or S2 can be a final state. You can have more than one state to be the final state. So let's start with this input. So initially when you start, you're in S0. When you're in S0 and you see a 0 and then you go to S2, so you're going to go to S2. So let's do it like this. So if you're in S0 and you see a 0, you're going to go to S2. And you're going to output a 0. And now we process this one. Now we're processing this. If you're in S2, you see a 0, you're going to stay in S2 and output a 0. Now if you're in S2, you see a 1, you're going to go to S1 and output a 0. Go to S1. If you're in S1, you have a 0, you output a 1 and go to S2. If you're in S2, you see a 1, you're going to output a 0 and go to S1. So now here's the output we get from this, and the final state we end up is S1 because we ran out of the input stream. Here's another one. What is the output of this finite state machine? Let's suppose that we start with S0. S0 and 0 will keep you in S0 and output a 0. S0 and 0 keep you in S0 and output a 0. S0 and 1 will take you to S1 and output a 0. S1 and 0 will take you to S0 and output a 0. S0 and 1 will take you to S1 and output a 0. S1 and 1 will take you to S2 and output a 0. S2 and 1 will keep you in S2 but output a 1. So here's the final output you get, and here's the final state you end up with. Because you ran out of the input stream, you won't be able to process anymore. So here's another one that we will take a look at, this one here. So we have two states, Q0 and Q1. Let's try to see what this finite state machine does. So if you send the input 1 and 1, we send a combination of inputs. Notice that the input alphabet is a 2-bit input. So if you set 1 and 1, then you're going to output a 0 and go to state Q1. When you're in Q1, when you see the combination 0, 1, which is this one here, you output a 0 and stay in Q1. When you're in Q1, you see 1, 1, you output a 1 and stay in Q1. When you're in Q1, you see a 0, 0, you output a 1 and go to state Q0. When you're in Q0, you see 0, 1, we output a 1 and stay in Q0. So notice the output I process from right to left. There's a reason for that. I'll tell you what it is. If you look at this one here, this is actually the sum of these binary numbers. 1 plus 1 is 0 and a carry 1. 1 plus 1 is 0 and a carry 1. 1 plus 1 plus 1 is a 1 and a carry 1. That carry gets added here, carry gets added here. So what you see here is a binary adder. So it actually goes from right to left, adding these numbers. So whatever the output it's giving you, if you give two binary numbers, this machine is going to give you the sum of those two numbers. So it's a powerful machine, as you can see. All right, so let's go to the next concept. The finite state automata. So finite state automata is something without an output. So let's take a look at this one here. So here, let's suppose that we call this S0 and S1, and you start with S0, and if you're in S0 and see a 0, you're going to go to S1. Notice that there's no output, there's no second thing here. If you're in S1 and you see a 0, you're going to go back to S0. If you're in S0, you see a 1, you're going to stay in S0. If you're in S0 and you see a 0, you're going to go to S1. S1 and 1 will keep you in 1. S1 and 1 will keep you in 1. And that's it. We run out of things. Now, what you see here is that we ended up in the state S1 at the end of the input stream. But what we say is that this machine actually represents a machine where the even number of zeros, if you end up in S0 after processing all of the string, that means you have even number of zeros. If you end up in S1, you have an odd number of zeros. By looking at this, you can see that it has an even number of zeros. So the output is only one decision thing. It says even number of zeros. All right, let's go to the next one. Actually, this is the same thing, so we just did that. Actually, this one is a little bit different machine. So for example, it's going to, no matter what you're going to do here, so let's say that this is S0, this is S1, this is S2, and S3. So we start from, let's start from, let's see here. Okay, so let's start from S0. S0, if you see a 0, you're going to go to S3. S3, if you see a 0, you're going to go to S0. S0 and you see a 1, you're going to go to S1. In S1, you see a 0, you're going to go to S2. And in S2, you see a 1, you're going to go to S3. In S3, if you see a 1, you're going to go to S2. And in S2, you see a 1, you're going to go to S3. So the final state you end up is S3. What the S3 says is that you have odd number of zeros and even number of ones. In fact, if you look at this, you can count odd number of zeros, 3 zeros, and even number of ones. So it's a very powerful machine, as you can imagine. This machine has no memory, but by using a state transition diagram, it can tell you, given any input stream, whether it has any one of these combinations of things. So this says even number of zeros and even number of ones. Even number of zeros and odd number of ones, and so on. So here they're asking us to build a machine, recognize all numbers that are divisible by 4. Now what we mean by divisible by 4 is that if you have a binary number, suppose we have a binary number like this. So as we know, this is 2 to the power 0, this is 2 to the 1, and this is 2 squared. And the next one would be 2 cubed, and so on. So any number that's represented by this bit stream is divisible by 4. So in order to recognize that something is divisible by 4, we have to build a machine that recognizes an input stream that ends with 0, 0. So it must ends with 0, 0. So how would you do something like that? Let's say if you get a 1, we're going to stay here. If you get a 0, we're going to move forward because we have seen now 1, 0. I want to get 2 zeros. If you get another 0, I'm going to move forward again to a final state called S2. So if your machine ends up in S2, that means I'm done. Let's think about this. Now, if you're in S1, if you see a 1, what should I do? I would say we need to go back to S0 because that means you have seen a 1. That means you're not going to get 2 consecutive zeros. But if you see a 0, you can go forward to the next state. So as you can see, this is completely determined by this machine because this machine will only end if you get 2 consecutive zeros in a row and it ends in S2. So here's a machine that can recognize if a number is divisible by 4. So here's another idea. This we would leave this as a sort of a practice. So this is going to check the parity whether they have an odd number of zeros or even number of zeros. Okay, so let's move on. So let me just do one other problem here. This says that we want to build a finite state machine that accepts the string AAB. So I'm going to start with a bunch of states, S0, S1, S2. And if I get an A, I'll go to S1. If I get another A, I'll go to S2. And then if I get another B, I'll go to S3. And the S3 is the accept state. So if you're lucky to get this sequence, you'll be going there. Obviously, you're not going to get this sequence So you have to decide what to do with the B and the other things. So for example, you don't want to go to S1 until you see an A. So if you get a B, you just stay there. Now when you're in S1, that means you have seen an A. If you see another A, you go to S2. But if you see a B, you must go back to S0 because you're not going to get two A's in a row if that happens. So we have resolved these two states, what happens when they see A and B. Now in S2, if you see a B, you go here, but if you see an A, what would I do? Now if you're in S2, that means you have seen two A's in a row. That's the only way you can be in S2. So if you see another A, just stay there because now you have seen another A. That means you have seen another A, that's okay. I'm just waiting till I get a B. So this is how the machine is completed. So you can see that every state except the final state has a transition for A and B. Now sometimes people write this machine as a table. So for example, S0, S1, S2, S3, and then try to define the transition for the alphabet characters A and B. So this one says S0 and A. S0 and A should go to S1, S0 and B should stay in S0, S1 and A should go to S2, S1 and B should go back to S0. S2 and A should stay in S2, S2 and B should go to S3, and that's the final state. Unless you want to repeat this machine, we don't really do anything in the final state. So this completes the demo of this thing. I think we have done a number of things where you would be able to design a final state machine.